Hi everyone, I'm Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Cheng Kung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. This is lecture 12-2. Maximum Considered Seismic Force 2. Maximum Considered Seismic Force is the seismic force corresponding to maximum considered earthquake. And here are some terminology. Maximum Considered Seismic Force Reduction Factor for Structural System due to ductility. In Chinese, 最大考量地震之结构系统地震力折减系数。Maximum considered seismic force corresponds to maximum considered earthquake, and the ductility capacity can be fully developed. Maximum considered earthquake is an earthquake level with 2% probability of exceedance in 50 years, or 2,475-year return period. And compared to maximum considered seismic force, design-based seismic force is the seismic force correspond to design-based earthquake, and only allowable ductility capacity can be developed. Design-based earthquake is an earthquake level with 10% probability of exceedance in 50 years, or 475-year return period. From seismic design codes, the maximum considered seismic force can be determined by equation 216C. Vm equal to I divided by 1.4 alpha y. I is the importance factor. Alpha y is the first yielding seismic force amplification factor, times SAM divided by FUM modification. SAM is maximum considered spectral acceleration. FUM is maximum considered seismic force reduction factor for structural system due to ductility. And W is the total structural weight. That's the dead load of the structure. In the previous lecture, 12-1, we have already talked about I, importance factor, SAM, maximum considered spectral acceleration, W, total structural weight, that's the dead load of the structure, alpha y, first yielding seismic force amplification factor. In this lecture, we will continue to talk about FUM, that's the maximum considered seismic force reduction factor for structural system due to ductility. For maximum considered seismic force, maximum corresponds to the earthquake level or maximum considered earthquake, and the ductility capacity can be fully developed. For design-based seismic force, it corresponds to design-based earthquake, and only allowable ductility capacity RA can be developed. For site class 1, 2, or 3, RA equal to 1 plus R minus 1 divided by 1.5. For Taipei Basin, the allowable ductility capacity RA equal to 1 plus R minus 1 divided by 2.0. My question is RA always less than R? Is allowable ductility capacity always less than ductility capacity R? From seismic design codes, the seismic force reduction factor for structural system due to ductility can be determined by equation 2-15. Maximum considered seismic force reduction factor for structural system due to ductility, FUM, depends on two factors. One is the fundamental vibration period, T, and the other is the ductility capacity, R. R here is the ductility capacity. The value of FUM can be divided into 4 segments according to TCM, and TCM is the corner period between short period and medium to long period. And here's the question for all of you. Is FUM always greater than FU? That means that the maximum seismic force reduction factor for structural system due to ductility FUM, is it always larger than FU? The design basis seismic force reduction factor for structural system due to ductility. That's my question for all of you. And FUM, the relationship of FUM against the structural period can be plotted in this way. When T is less than or equal to 0.2 TCM, FUM increases linearly with the structural period T. When T, the structural period, lies between 0.2 TCM and 0.6 TCM, FUM is a constant equal to square root of 2R minus 1. When the structural period lies between 0.6 TCM and TCM, it increases with the structural period. It increases linearly with the structural period T. And when T larger than or equal to TCM, FUM is a constant and equal to R. And this one is a typing mistake. It should be TCM. This should be TCM. This should be TCM. The longer the period, the larger the reduction factor. Therefore, the more reduction for the seismic force Vm. The longer the period, the larger the FUM. Because FUM is denominator for the calculation of maximum considered seismic force Vm. The larger the FUM, the smaller the Vm. When the structural period is very, very short, the structure becomes very, very rigid. Even though the structure possesses ductility, because there's no deformation, the ductility cannot be developed, so that the reduction factor FUM is close to 1, no reduction for seismic force Vm. When the structural period is very, very long, the structure is flexible, so that the ductility can be fully developed. Therefore, the reduction factor FUM is close to R. Then we have maximum reduction for seismic force Vm. Therefore, we have the smallest value for the maximum considered seismic force. The higher the ductility capacity R, the better the ductility. The larger the reduction factor FUM, the higher the R, the larger the FUM. The larger the FUM, the smaller the Vm. Therefore, more reduction can be obtained for seismic force Vm. When ductility capacity R equals 1, when R equal to 1, square root of 2R minus 1 equal to 1, R equal to 1, then FUM is a straight line with constant value equal to 1. Therefore, the structure has no ductility. Therefore, the reduction factor FUM equals 1, and no reduction for the seismic force Vm. And how do we have the value square root of 2R minus 1? And here are two structures. One is the elastic structure in blue. The other is inelastic structure. Here is the force displacement relationship under maximum considered earthquake. For elastic structure, the force of the structure varies linearly with the displacement delta. And the maximum force is VE, and the maximum displacement is delta E. For the inelastic structure, when the displacement becomes delta Y, the structure yields and remain the force Vy Therefore, it is simplified as a elastic, perfectly plastic structure. When the structural period lies between 0.2 T0M and 0.6 T0M, the criteria of equal energy is satisfied. That means that the area under the elastic structure equal to the area under the curve of the inelastic structure. For the elastic structure is a triangle. Therefore, the area of the elastic structure equal to half times VE times delta E. This is the area of the triangle. This is the energy of the elastic structure. The energy of the inelastic structure is the area under the red line. It's a trapezoid. The area of a trapezoid equal to 1/2 times Vy. Vy is the height of the trapezoid. Times R delta Y minus delta Y is the length of the top base, and R delta Y is the length of the bottom base. By the criteria of equal energy, the energy of the inelastic structure equal to the energy of the elastic structure. And half cancel out, then we have Vy times R delta Y minus delta Y plus R delta Y equal to VE times delta E. Delta E, by the similarity of triangle, delta E equal to VE divided by Vy times delta Y. Therefore, delta E here is substituted by VE divided by delta Vy times delta Y. And delta Y, delta Y, delta Y cancel each other. Then we have VE divided by Vy squared equals to 2R minus 1. Therefore, we have VE divided by Vy equal to square root 2R minus 1. FUM equal to square root of 2R minus 1. If we don't allow the structure to enter into inelastic range, that means that the structure remains elastic during maximum considered earthquake. Then the force, the seismic force for the design of the elastic structure is VE. If we allow the structure to enter into inelastic range, and the ductility of the structure can be up to R, therefore the ratio of the ultimate displacement to the yielding displacement equal to R, then we can just use Vy for the design of the inelastic structure. Therefore, we use VE for the design of elastic structure, and we use Vy for the inelastic structure. Therefore, the ratio between VE and Vy equal to square root of 2R minus 1. That means that if we allow the structure to enter into inelastic range, we can use less seismic force for the design of the structures. Therefore, when the structural period lies between 0.2 T0M and 0.6 T0M, FUM, the seismic force reduction factor, equal to square root of 2R minus 1. And how do we get the value R? When the structural period is larger than or equal to T0M. Here we have two structures. Under maximum considered earthquake, we have two curves here. One is the force relationship of the elastic structure. One is the curve for the relationship between the force and displacement of inelastic structure. If the period is long, therefore the structural period, there is the structural period larger than or equal to T0M, the criteria of equal displacement is satisfied. Therefore, for the elastic structure, the maximum displacement equal to delta E. For the inelastic structure, the maximum displacement equal to R delta Y. Under the criteria of equal displacement, R times delta Y equal to delta E. By similar triangle, delta E equal to VE divided by Vy times delta y. Therefore, the delta E here can be replaced by VE divided by VY times delta Y. Delta Y and delta Y cancel out. Then we have VE divided by Vy equal to R. Then FUM equal to R. That means that when the structure has to remain elastic during earthquake, then we have to use VE seismic force for the design of elastic structure. If the structure are allowed to enter into inelastic range, that means that when the displacement of structure reaches delta Y, the structure yields, then we can have less seismic force for the design of the structure. The condition is that the inelastic structure have the ductility equal to R, the ductility capacity. That's the ratio of the ultimate displacement to the yielding displacement. Therefore, when the structural vibration period is long enough, that is larger than or equal to T0M, then FUM equal to R. The seismic force reduction factor, FUM equal to R. And the curve here is the displacement force relationship of a structure under earthquake. And the curve here can be approximated by elastic perfect plastic system. Therefore, we have delta Y is the yielding displacement and delta U is the ultimate displacement. The ratio between delta Y and delta U and delta Y, that's the ultimate displacement to yielding displacement equal to R. Therefore, R is defined as the ratio between ultimate displacement and yielding displacement. The figure here is taken from Seismic Design Codes figure C2-1. From Seismic Design Codes table 1.3, we can look up the ductility capacity for different structural systems. And here's an example. If the structural system is reinforced concrete structure with moment-resisting frames, according to this table, the ductility capacity R equal to 4.8. And here we back to the example. So far we have I, importance factor, I equal to 1.0, spectral acceleration, maximum spectral acceleration, SAM equal to 1.32. The total weight of the structure equal to 146.05 ton force. And the first yielding amplification factor, alpha Y equal to 1.0. And a residential building located at Ruishui Township, Hualien County. The building is reinforced concrete structure with moment-resisting frame. The question is to find maximum considered seismic force reduction factor for structural system, FUM. From Seismic Design Codes, Table 1.3, the ductility capacity of reinforced concrete structure with moment-resisting frame, R equal to 4.8. Therefore, the ductility capacity for the building here equal to 4.8. And from previous lecture, we have RA equal to 3.533. Therefore, in this case, R is larger than RA. And we have a question here. Is RA less than R or R greater than RA? For this case, it is true. R is greater than RA. And then we back to the example. So far we have I, importance factor, W, total structural weight, SAM, maximum considered spectral acceleration, R equal to 4.8, alpha Y equal to 1.0, the structural vibration period equal to 0.268 seconds. And the question is to find the maximum seismic reduction factor for structural system. From previous lecture, we have T0M equal to 0.658 seconds. And the structural vibration period here falls into the range between 0.1316 to 0.3948 seconds. Therefore, FUM is a constant equal to 2.933. FUM, the maximum considered seismic force reduction factor, equal to 2.933. And from previous lecture, we have FU, the design basis seismic force reduction factor for structural system, FU equal to 2.463. And in this case, FUM is larger than FU. Therefore, in the case we consider, FUM is really larger than FU. But is this true for other cases? That's my question. And this equation is taken from Seismic Design Code equation 2-15. And we move to the modification of SAM divided by FUM. When SAM divided by FUM is smaller than 0.3, no modification is necessary. Therefore, the ratio after modification equal to the ratio without modification. Therefore, SAM divided by FUM modification equal to SAM divided by FUM without modification. When the ratio SAM divided by FUM is larger than 0.8, then we have SAM divided by FUM modification equal to 0.7 SAM divided by FUM. This is modified to be 70%. When SAM and FU divided by FUM is between 0.3 and 0.8, and we use linear interpolation to make the curve continuous. And the equation here is taken from the Seismic Design Code equation 2-16D. And here's my question. Is the ratio SAM divided by FUM modification larger than SAD divided by FU modification? Is the factor for maximum considered earthquake larger than the ratio for design basis earthquake? That's my question. Is it always true? And here's the curve between modification and without modification. When SAM divided by FUM is less than 0.3, the modification one equal to the one without modification. Therefore, the modification one equal to the one without modification. When SAM divided by FUM is greater than 0.8, greater than or equal to 0.8, and is reduced to the 70% of the one without modification. Therefore, the ratio with modification is 70% of the ratio without modification. When SAM divided by FUM lies between 0.3 and 0.8, and we use linear interpolation to make the curve continuous. And SAM divided by FUM modification equal to 0.52 SAM divided by FUM plus 0.144. The shorter the vibration period, the higher the spectral acceleration. The higher the spectral acceleration, and the lower the reduction factor. Therefore, the ratio between SAM and FUM when the vibration period is short is large. When the vibration period is short, the ratio is large. And the shorter the vibration period T, the higher the effect of soil structure interaction. Therefore, it will lower the ground intensity. Therefore, when SAM divided by FUM is high, modification and reduction is necessary. And here, back to the example. So far, we have I, importance factor, total weight of the structure, first yielding amplification factor, maximum considered spectral acceleration, and maximum considered seismic seismic force reduction factor. And a residential building located at Ruishui Township, Hualien County. The question is to find the modification for the ratio between SAM and FUM. SAM divided by FUM equal to 1.32 here, divided by 2.933 equal to 0.4501. It is larger than 0.3, is larger than 0.3, so that modification is necessary. According to the Seismic Design Code equation 2-16D, SAM divided by FUM modification equal to 0.52, SAM divided by FUM plus 0.144 equal to 0.3780. And from previous lecture, we have SAD divided by FU equal to 0.4612, and the modification of the ratio SAD over FU equal to 0.3838. Compare with the design basis modification factor. The modification factor for the maximum considered earthquake is less than the modification factor for design basis earthquake. Therefore, the question here is not true. SAM divided by FUM modification is less than SAD divided by FU modification. But is this always true? Is there any exception? That's my question. And here's the summary for the procedure to determine maximum considered seismic force, VM. Step 1, from the usage of the building, look up section 2.8 of the Seismic Design Code, we can get the importance factor I, maybe equal to 1.5, 1.25, or 1.0. Step 2, from the seismic zone, fault distance, site classification, the vibration period of the structure, we can get the maximum considered spectral acceleration, SAM. Then we move to step 3, from the dimension of the structure and the dimension of its members, we can get the total weight of the structure, that's the dead load of the structure W. From step 1, 2, 3, we can have I, importance factor, SAM, maximum considered spectral acceleration, W, the total structural weight. And then we move on to step 4, from structural system, design method, and loading combination. We can look up section 2.9 of the Seismic Design Code to get first yielding amplification factor alpha Y. And then we move to step 5, from the structural system, look up table 1-3 of the Seismic Design Code, we can get the ductility capacity R. From R and the vibration period T, according to equation 2-15 of the Seismic Design Code, we can get the seismic force reduction factor FUM. From step 1, 2, 3, 4, 5, we have the importance factor I, maximum considered spectral acceleration SAM, total structural weight W. First, yielding amplification factor alpha Y, and maximum considered seismic force reduction factor FUM. From the ratio of SAM to FUM, according to equation 2-16D of the Seismic Design Code, we can get the modification of the ratio, that's SAM divided by FUM modification. From step 1, 2, 3, 4, 5, 6, we have the I, importance factor, SAM, maximum considered spectral acceleration, W, total weight of the structure, alpha Y, first yielding amplification factor, FUM, maximum considered seismic force reduction factor due to ductility, and also the modification of the ratio between SAM and FUM, so that according to equation 2-16C, that's this equation of the Seismic Design Code, we can get the maximum considered seismic force, VM. And here's my question for all of you. Is VM always larger than V is maximum considered seismic force always larger than design basis seismic force. And then we back to the example. So far we have I, importance factor, W, total weight of the structure, alpha Y, first yielding amplification factor, SAM, maximum considered spectral acceleration, FUM, maximum considered seismic reduction factor due to ductility, and the modification of SAM divided by FUM equal to 0.3780. Then the question is to find maximum considered seismic force VM. This is a residential building located at Ruishui Township, Hualien County. According to the equation 2-16C of the seismic design codes, VM equal to I divided by 1.4 alpha Y, I equal to 1.0 divided by 1.4 alpha Y equal to 1.0 times SAM divided by FUM modification. The modification of the ratio is 0.3780 and times W. Therefore, VM, the maximum considered seismic force, equal to 0.270 W, equal to 39.4 ton force. And from the previous lecture, we have already got the design basis seismic force V equal to 40 ton force. And compare these two, then we can have the maximum considered seismic force is less than the design basis seismic force. Therefore, the equality here is not true, at least in this case. The maximum considered seismic force is less than the design basis seismic force. But is this all true? Is there any exception? And here's the seismic design code of the building, published in 2011 by the Ministry of Interior. And here's the website to download the design codes without any charge. And videos for Lecture 1, Lecture 2, Lecture 3, Lecture 4, Lecture 5, Lecture 6, Lecture 7, Lecture 8, Lecture 9, Lecture 10, Lecture 11, Lecture 12. And 12-2, the videos on maximum considered seismic force 2, the English version is the current one, is under production. It will be uploaded to the YouTube later on. And in this lecture, we have considered maximum considered seismic force, VM. Maximum considered seismic force corresponds to maximum considered earthquake, and the ductility capacity can be fully developed. And then compare with design basis seismic force. Design basis seismic force corresponds to design basis earthquake, and only allowable ductility capacity can be developed. And here's some question for all of you. Is SAM always larger than SAD? SAM is the maximum considered spectral acceleration. Is maximum considered spectral acceleration always larger than design basis spectral acceleration? That's the first question. Another question is FUM larger than FU? FUM is the maximum considered seismic force reduction factor, always larger than design basis seismic force reduction factor. That's the second question. And the third question is the maximum considered seismic force always larger than the design basis seismic force? In general, SAM is larger than SAD. Therefore, the numerator SAM is larger than SAD. And in general, FUM is larger than FU. The denominator for VM is larger than the denominator for V, because both the numerator SAM, the denominator FUM is larger than the corresponding ones for the design basis seismic force. Therefore, it's not always true that VM is larger than V. It may be case by case. That's all for this lecture. Thank you. See you next time. Bye bye.